So this is basically a review here, and it's just what I had just done was introduce the tension equation, and you just had to use more equations, more unknown. But now we're going to go review, and it's everything's written here, okay? Not everything, but a lot of stuff. The continuity equation gives you that area times velocity is a constant. And I often say that this is the most forgotten equation. It's overlooked, the most overlooked equation. And it's the one that relates the velocity to the area, cross-sectional area, when you do Bernoulli's equations. You can also use it for PHYS law. And what it leads to is the idea that the larger the cross-sectional area, the slower the velocity. Or the way I like to point out is when you put your finger on the garden hose, the velocity goes up, you spray people, right? And so the narrower the cross-sectional area, the larger the velocity becomes, okay? At that point. Bernoulli's equation is this one where those three terms add up to a constant. We never care about what that constant is. But what we do is we add up those three terms at one portion of some plumbing and another portion, and we compare them. They're equal, and that's very useful. And like I pointed out, that sometimes you cancel out the heights on both sides because it's horizontal, or if the cross-sectional area isn't changing, you could just cancel the velocity term because same cross-sectional area. Okay, area means that V1 is equal to V2. Okay. That's very useful. You plug that into Bernoulli's equation, simplify it quickly. Okay, the larger the height, the smaller the pressure when V is constant. So if we had this tube that I just drew, as it gets higher, if the area stays constant, the velocity stays constant. Okay, the larger height, the smaller the pressure. Pressure is going to be higher at the bottom, lower at the top. We keep on going. So, look, you can go read more through this. Bernoulli's equation, PHYS law. So PHYS law is what you use when the viscosity, okay, is non-zero. It's not equal to zero. If it were zero, this formula wouldn't work. And this is a formula that allows you to figure out what happens in these sort of problems that look like this, right? Where you have the water, okay, and we can say the height, okay, and we have some flow coming out. What you're going to need is the length and the radius, okay, and the height, and you can figure out flow rates. Remember that delta P over L is pressure gradient. Okay. Reynolds number is the next formula we learned, and it has to do with turbulence, so turbulent flow. And remember, I pointed out that you've got to be very careful, okay? If someone changes, if you change D, you may also change what? The velocity. Okay, very important, right? So if someone told you you have a constant flow, then you're going to have to remember that Q is equal to velocity times area, which is equal to velocity times pi r squared, which is equal to velocity times pi times the diameter squared over 4, right? And you might need to use this equation, the most overlooked equation, to make sure that if, let's say, you double the diameter, you may cut the velocity down, okay, as the areas go, okay? Keep on going. Pulsatile flow, and I'm going to give you some more examples about that, okay? And you do those and you're going to get it, okay? So it always has a plot, and it should have a plot of Q, which is the instantaneous flow rate versus time over one beat. And the idea is we're doing these triangular, the area of a triangle, and we characterize and analyze analyze the plot. And then there was this one weird thing that you have to remember, that you have to convert. That you have to do this conversion where you say TP corresponds to 360 degrees. So if you measured something in degrees, you have to convert. TP over 360 serves as a conversion factor. Okay, and I'm going to do those examples, you'll see. Then we talked about elasticity in blood vessel walls, and there's that formula. Tension is equal to delta P times R. Okay, and general rules to keep in mind for continuity. If the cross-sectional area goes up, the speed goes down. I repeated that. If H1 is equal to H2, the speed goes up, the pressure goes down. It's just other ways of saying the same thing. Okay. For the constant velocity, if the elevation goes up, the pressure goes down. You can make these sort of observations. Now we're going to do we're almost done, pulsatile flow problem. And I'm going to call it example 2. Let's read it.